right, welcome to the notes for lesson 5.4. So this is where we're going to get into applications of quadratics, why we've been studying quadratics, especially why we care so much about the vertex. We keep telling you how important the vertex is and the x-intercepts, that they're the most important things when you use quadratics in real life, in real world problems. So now we're going to give you some examples of that. So there are many ways that quadratics can be used to solve real world problems. It'd be impractical to discuss all of them, but here's a few tips that can guide you as you solve some of these types of problems. So first of all, finding the vertex. So with the vertex, I know we've talked about the vertex a lot. The vertex is, as you know, the minimum or maximum point of your graph. So you're going to use the vertex when you hear phrases like find the minimum cost or the maximum cost or what is the maximum height. So anytime you hear something about the maximum or the minimum, you want to think vertex. For x-intercepts, those are going to be problems where you're looking for where the model equals 0, such as where it hits the ground or where the profit is 0. So think of if you had a rocket ship that took off and then when did it land? That's when it hit 0. So that would be an x-intercept. So those are types of things you're going to look for when you're going to look for the x-intercepts. Lastly, just using your f of x. And what that means is your y values and your x values. So I know we haven't talked too much about function notation. That's when we use that f of x instead of using a y. I made another short little video explaining that. So if you're confused about this notation right here, instead of using a y, you can check out that video. But basically what this means is sometimes they're going to ask you for what happens at a certain x value or what happens at a certain y value. And so in that case, you'll either plug in that x value or plug in that y value and solve and see what happens. So that's going to happen. You're going to look for questions such as like at what time or what is the cost for producing a certain number. So they'll give you a certain number or they'll ask for a certain at a certain time. So those are some hints to kind of tell you what kind of things you're going to be looking for. Again, though, word problems are all about problem solving. You guys have the tools to understand quadratics, but now you need to put your thinking hats on and think about what these problems are really asking you. So let's do some examples. So the first one says a cannon fires a cannonball at a castle. So stop right there. I know you should read the whole thing, but let's go ahead and draw a little picture. I am not an artist. Let's draw a little castle. Here's my little castle, and we have a cannonball. Here's a cannon. It's going to shoot a cannon at this castle. All right, so I have a little picture. Hopefully you guys can draw something that will give you an idea of what's going on there. So it says the height of the cannonball can be modeled by this equation right here. Okay, that makes sense. That's a quadratic equation, which is a parabola, and that's what I drew, a parabola. That's what kind of a cannonball path would look like. And it says where h of t is the height in feet of the cannonball t seconds after it's fired. So I want to stop there for a second and talk about my t and my h of t. So there's no x and there's no y, but if we were to draw this on a graph, in fact, let's put in some axes here. Well, not yet. I'll do that in a second. So one of these is our independent variable, and that's going to be like our x, and that's the seconds. We can, how high the cannonball is dependent on how long it's been fired. And so our t is going to be like our x variable, the independent variable on the x-axis. And then the h of t is the dependent variable. So it's going to go on our y-axis. All right, so let's look at some of the questions here. Number one, or part A, what is the maximum height of the cannonball? All right, so maximum height, looking at your notes, what should we be looking for? we're going to look for the vertex. Maximum height, we're going to be looking for the vertex. So we're looking for this point right here. Okay, so we're going to be looking for a vertex. And when it says the height is the h of t part. So that's going to be the y value of our vertex. So y value of vertex. All right. What about b? At what time does it achieve that height? Well, again, we're talking about that maximum point, so we're still talking about the vertex, but now we're talking about the time. The time is our x value of our vertex. So both of these are talking about this point right here, that vertex point, but one of them wants to know when it's going to get there, the time, and one of them wants to know how high it will be, and that's our y. All right, I did say we should put in some axes. Let's go ahead and do that. So you want to think about, so time, when did time start? Time started when the cannonball left the cannon, and then also as far as height, that's kind of your origin too. So your origin should be right here at this cannonball. So I'm going to draw my axes going right through, well, right through the cannon. All right, so there's my origin. Okay. All right. How many seconds pass from the time it's fired until the cannonball hits the castle? And it says, assume the height of the castle and the cannon are the same. And that would have been nice to know when you drew it. That's kind of how I drew it, though, because I had already read the question. So this point right here is level with this point. And because we have a picture, I bet you guys can tell what those points are. They're going to be our x-intercepts. So we know one of them, it's actually our y-intercept and our x-intercept because it's right there at the origin. But this one here that we want to find, when it hits the castle, that's going to be our other x-intercept. All right, it's our x-intercept. And we want to know how many seconds pass. So we want to know a time. And so the time is going to be that x value because the time is the x value. All right. And then let's see. Let's stop there because before we go on to D, D's a little different. Right now we haven't actually found any info. We've just kind of gotten an idea of what we're looking for. So we have the equation, and we could do this a couple ways. You guys know how to take an equation and change it into a different form or use some of the formulas we have to find vertex or x-intercepts. We're going to give you an easier way to do it on these problems because we want you focusing on problem solving. We know you know how to do the algebra and to do the manipulating the equations, changing forms. Right now, we just want you focused on thinking about the problem solving. So what I want you to do is on a computer, on your Chromebook, you're going to go to, and I think you can do it on a phone too, you're going to go to right up here, desmos.com.calculator. So type that into a search bar. I'm going to go ahead and let's see. Okay, so it's going to look something like this. You'll have a graph on one side and you'll have an area where you can enter in an equation over here. So you'll touch that little, you'll click in that little box where it says 1 and you'll be able to type in an equation. So type in the equation of our cannonball. So let's see, I have it right there. It is -16 and instead of t, I'm going to put x squared plus 224x. All right. And I'm going to make this full screen now so I can see it. Here we go. Okay. So, and I can kind of zoom out till I can kind of see my my parabola. Now this parabola does not look like the one I drew. It is much skinnier and much taller. Remember, mine was just a sketch. And so you can zoom in. You can also click over. I can't kind of highlight what I'm doing here, but if you go in the top right corner, there's a little wrench. If you click on that little wrench, you can adjust your axes. I'm going to change my my window here. I'm going to go from like -25 to +25, just so I have maybe a window that looks a little easier to see. All right, so this is my parabola. So this is my, at the origin at 0, 0, that is my canon, over, down, and I'm going to touch, if you, the great thing about Desmos is if you touch on the graph, if you click on it with your mouse, it'll show you a point, and if you click it again, it'll tell you what that point is. So this point down here on the right that I just clicked, 14, 0, that is my x-intercept. So if I go back to my notes, sorry, I'm going back and forth here. Let's see. That is my x-intercept. So right here, my x-intercept is 14, 0. That means at time 14 seconds, the cannonball has hit the ground, or it's hit the castle in this scenario. It's hit the same level that it started at, where the cannon was. So how many seconds pass from the time it's fired until the cannonball hits the castle? 14 seconds. So that's the answer to that one, 14 seconds. So we're going to just look at the graph on Desmos and let it give us the information for these values, the x-intercept and the vertex. But you guys need to be able to interpret the graph and see what they each mean. All right, so the other thing we needed to find for part A and B was the vertex. So I'm going to go back to Desmos, and so I'm going to click on that top point, that vertex, and the vertex is at the point 7, 784. All right, so vertex is at 7, 784. But again, that's just the point. We need to actually answer the question. What is the maximum height of the cannonball? So one of those was the height. The y value is the height. So the maximum height is 784. It's in feet. So we have to use our unit. 784 feet. That is our max height. So that's the answer for part A. And the answer for part B is, at what time does it achieve that height? And the answer is at 7 seconds. So at 7 seconds, the cannonball is at 784 feet. And then at 14 seconds, it hit the castle. All right. The last question, part D, it says, at what 2 times is the height of the cannonball equal to 720 feet? So this is this last part of the notes where it says using f of x to find values. So what that means is we're going to think this number that they're giving us, 720 feet, is that an f of x or is that an x? It's in feet, so that means it's going to be an h of t. It's a height. So we're going to plug it in as a height. So we can say that 720 feet equals some value for t. So -16 t squared plus 224 t. So we're plugging it in. We're plugging it in place of the h of t in our equation. So again, we could use our algebra. This is an algebra problem that you could have done last quarter when you were solving quadratics. We can solve this, and that's fine if you want to do it that way. But we are going to use Desmos again to do it. So I'm going to go back to Desmos. I'm going to click on 2 and put a new equation. My equation that I'm going to put is just y equals 720. That was the number we were looking for, right? Let me double check. Yep, 720. So it drew a line for me, and where that line intersects, there's dots, and I can click on those dots, and it happens at 5 seconds and again at 9 seconds. So at 5 seconds, the cannonball is at 720 feet, and also at 9 seconds, it's at 720 feet. And we could plug 5 in for t. We could plug 5 in right here for t, and here, if we wanted to do that. we could check our work and it would equal 720. And we could also do the same thing with 9 and it would work. But we're going to use the Desmos and just trust that it works. And what we're really doing here is making sure we understand the idea behind what's going on with the graph. All right, example number 2. From a stop position, a car starts to accelerate at a constant rate. Has a table showing us the info, and then it has the distance can be modeled in terms of time by this equation. So the independent variable is time, and then the distance is dependent on how long the car has been traveling. So they're asking us about how far the car has traveled after 7 seconds. At what time will the car have traveled 30 feet? And then if the car maintains this acceleration, how far will it travel? Will it have traveled after 60 seconds? And then explain why this would or wouldn't be reasonable. All right, so going back up to our notes, and I do not have them highlighted. Let's see. So when it's giving us specific numbers at what time or 300 feet, 60 seconds, we are going to be using just the equation itself to find these. So we're using f of x to find the values. So we could actually do most of these algebraically. So I'm going to write them as equations. So how far has the car traveled at 7 seconds? So we want to know how far, that's the distance. So we want to know the distance at 7 seconds. So we're going to put 7 in for what the time is. So then we'll put 7 in again wherever there's time. So this is what we want to know. So we could go ahead and just plug that into our calculator and we would get the answer. So let's see. 49 times 3 equals 147. All right. So 147, we are in feet. So 147 feet. Make sure you always are putting your units. At what time will the car have traveled 300 feet? So now what they're giving us is they're giving us the feet. So we know the distance. So we know the distance is 300, but we want to know the time. So we don't know the t. So 300 is going to equal 3t squared. So again, we can solve this algebraically. So we can divide both sides by 3. We get 100 equals t squared. Take the square root. We don't have to consider the negative because time isn't going to be negative, and we have 10 equals t. So that's in seconds. So at 10 seconds is when the car will have traveled 300 feet. Okay. Part C, if the car maintains this acceleration, how far will it have traveled after 60 seconds? All right. So 60 seconds. So this is the same question as A. So we want to know the distance after 60 seconds. That's going to equal 3 times 60 squared. Now I actually have to get my calculator out. Probably Mr. Reed could do this one in his head, but I'm not going to try. Okay, so 60 squared equals, I should know this, 3,600. And then we're going to times that by 3. And that's going to equal 10,800. So our distance at 60 seconds is going to equal 10,800 feet. So that is our answer for part C. All right. Before we talk about why that would or would not be reasonable, we didn't actually look at a picture of this one. I'm going to go back to Desmos. And I'm going to put this equation into the graphing calculator here. So 3x squared. And let's zoom out a little bit. Okay. All right. So it's a parabola. We're not really going to pay attention to the part of the parabola that's before 0 because remember, our x is time, and so we're starting at 0. So we're really only looking at the positive side of this. All right, so we can look, I I keep thinking I can draw on this, but I can't. We can draw some other lines though. We can use the, okay, so we can draw the line x equals, nope, let's do y. Okay. Y equals, nope, yeah, x equals 7. That's what I wanted. I knew I was doing x. Okay, x equals 7. So at 7 seconds, we can see, and we can zoom in and find that where it connects. So 147. So that's what we found, right? That was the point we said where at 7 seconds, the car had gone 147 feet. Now let's try y equals, because that's where they gave us the y. We wanted to know how long it took for it to go 300 feet. So when y equals 300 feet, so now we're going to see that point on the graph right there. So that's 10 seconds. 10 seconds, it's gone 300 feet. And then the last one was we wanted to know when x, I'm just going to get rid of those because we don't need to see those. When x equaled 60 seconds. So that's way out here. So that means we're going to have to zoom way, 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 way. And we knew what it was because we did it algebraically. It's going to be right about there somewhere. There we go. 60 seconds, 10,800 feet. All right. So sometimes it's easier to do this on Desmo. Sometimes it actually is easier to do it algebraically. So the last part of that question, though, explain why this would or wouldn't be reasonable. So 60 seconds, that's a minute. And in that minute, this car has gone, starting from nothing, 0 to it's ended up going almost, actually a little over 2 miles, because a mile is 5,280 feet. So it's gone over 2 miles in 1 minute. So that's an average of 120 miles per hour. But it wasn't starting off at that speed, obviously, so it's going faster than 120 miles an hour at this point. So definitely not reasonable. So not reasonable. Okay, not reasonable. All right, moving on. Let's do example 3. So again, this is going to be a totally different situation. All of these word problems, you're just going to have to think about them. There's not a pattern, except for the hints at the top, the tips, to think about what parts of the parabola you should be looking at. All right, so our equation here in this case, right here, there's our equation. So I'm going to highlight that. Okay, a company has determined its cost for producing a certain item is modeled by this equation, where C of X is the cost per item in dollars when X items are produced. So our independent variable X is how many items they're producing. So they're making something, they're going to make X of them, and it's going to cost a certain amount per item. So let's say they're making t-shirts, and the more t-shirts they make, the cheaper it is per shirt, for example, or the cost depends on how many they make. So this equation tells us not the total cost, it tells us how much per item. So C is the cost per item. And it depends on how many items are produced. All right. So, first question, what is the cost per item when 50 items are produced? So they're telling us a number. They're telling us an X value. When 50 items are produced, that's right there. That is an X value. So they're saying, what is C of 50? They're saying, what is the C of X when X is 50? So all we have to do is plug that 50 into our equation. And again, you can do this on the calculator, not even graphing, just plugging it into your regular calculator. We can go C of X equals 0.1, and then wherever you have an X, plug in 50 squared, minus 20, 50, plus 13, 50. Let me grab my calculator here. You guys can do this too. Okay. 0.1 times 50 squared minus 20 times 50 plus 1350. Make sure I plugged it all in right. Make sure what's in my calculator looks like what's on what I wrote down. Okay, and I got $600. Okay, so definitely not t-shirts because $600 per item. So this is in dollars, so I'm going to use my unit, $600 per item. Okay, so that is my cost per item when 50 items are produced. All right, cool. All right, next question. How many items should be produced in order to minimize cost? So there's a keyword here. I hope you guys found it, minimize. So when we see the word minimize, what are we thinking? What word should stand out to us? Hopefully you remember that that is going to be the word vertex. Minimum cost, we want to look for the vertex. So we want to find the vertex of this parabola. I'm going to go to Desmos to graph this parabola because I'm not going to try to find the vertex of this on my own. So I'm going to go to Desmos. All right, let's clear out my old equations. And it was 0.1. You know, I don't have to do this, but sometimes I like writing y equals 0.1 x. Hold on. X squared minus 20x plus 1350. Okay. All right, so here's my parabola. All right, so I definitely see that it opens upward, so it has a minimum point, and that's my vertex. That's the point I want to find. So as you see, as you touch the graph, different points show up. So this point right there, that's our y-intercept. And I don't think it asked about that, but that is an interesting point. That would be the cost of producing 0 items. So it'd cost $1,350 to produce 0 items. But we want to know what's the least amount per item. Okay, so if I produce, remember, X is my number of items. So if I produced 100 items, my cost per item would be $350 per item. All right, so let's go back. So that is, all right. So how many items should be produced in order to minimize the cost? Okay, so 100 items. That was what it looked like. It said at 100 items, that was when the cost was minimum. So 100 items should be produced. And then what was the minimum cost per item? The minimum cost per item was $350. That was the minimum cost. All right. So hopefully with those 3 examples, you guys can have an idea of some of the ways to look through these problems. Not all of them are going to be the same on your homework, but you can put on your, put to use your problem solving skills, and good luck.